Okay, we're down to the final 3 class periods. Yay! Okay, this is the time of year when everyone's exhausted, and when I was advising students at the beginning, telling them if they took 5 courses in a semester, they would just never survive, and nobody believed me, and now they understand that even with 3, it is very exhausting, and if one of those 3 is Rob 550, it's super exhausting. Yeah. Okay, so we're working on sequences. We want to have iterative means of developing solutions to problems that are sufficiently complex that we cannot just write down a set of linear equations, for example, in order to generate its solutions. So then the idea is, if we're going to iterate, we're building a sequence, and we want to understand when does there exist a point such that that sequence converges to it. And then we would like the point to which it converges to be the point we're interested in. So we've been starting and making various attempts at tying that to concrete examples. So the first thing we did was we wrote down very carefully what does it mean that a sequence converges to a point in terms of every epsilon, no matter how small, I can go sufficiently far down the sequence, and then for all points beyond that, I'm never farther than epsilon away from my point of convergence. Then we said, no, that's beautiful, but if I'm really trying to prove that my algorithm produces a solution, I don't have this in hand. And so we had the notion of a Koshi sequence. And so a Koshi sequence is similar to a converging sequence, except instead of comparing the terms to this limit that we don't have in hand, we compare the terms to one another. And it's similar to this in that if the sequence is converging and I let my m get really large while the n is fixed, then I'm capturing the same notion, okay? And so the notion of Koshi is no matter how small of an error I give myself, as long as it's positive, I can go sufficiently down the sequence such that the terms all pile up and never get farther away than that epsilon. And so that begs the question, do all Koshi sequences converge? And the answer is no, but kind of almost. Okay, so if you have a set with the property that it is complete, which by definition means that every Koshi sequence you build from elements of that set has a limit in S, then you get the Koshi property working. And the magic thing is that if you're in a finite dimensional norm space and your set is closed, then it's automatically complete. So we have a concrete way of checking cases where Koshi sequences always have limits. And then in the infinite dimensional case, when the set being closed is not sufficient to get completeness, we have this fact that is not on any final exam in Rob 501, that our norm space fits tightly into another one that has the completeness property. So that's something that Banach established when he started studying these types of spaces. So not every Koshi sequence has a limit, but every Koshi sequence can have a limit in a slightly larger norm space. Every norm space has a completion. So that's what I mean by no, but kind of almost. So, but for you on your exam, if the statement says, does every Koshi sequence have a limit, the answer is no. If it's finite dimensional, does every Koshi sequence have a limit? Yes, okay? Things like that. It's very cut and dried. We like to use sequences to characterize various properties, as you'll see. It's a very powerful notion as well. And so we first defined a limit point of a set. And just to make things more clear on my existence, I grouped the two properties together. Okay, so X, a point in X is a limit point of the set S if there exists a sequence built from elements of S that converges to that point. Okay, so X0 is now a limit point of S. It may not necessarily be in S, but it's a limit point in S. I can approximate X0 arbitrarily closely with elements of S. And then from our work on the closure of a set, the closure of a set is the set of all points that are distance 0 from the set. And so we have the equivalence between a set being closed and it contains all of its limit points. It's really the same concept, expressed in different terms, but it's the same concept. How do we go about generating Koshi sequences? One way is via a contraction mapping. So a function that takes a subset S to itself is a contraction. If I find a number C, hopefully that says strictly less than 1, greater than or equal to 0, such that if I take any 2 points in the set, I apply P to them, they're now closer than they were originally. They contract by, say, 0.9 or 0.99. And then any mapping with this property generates Koshi sequences, and hence if S is complete, this sequence has a limit and it will satisfy X star equals P of X star. It's a solution of the equation X equals P of X. So that's a super powerful way of constructing iterative solutions. And Newton-Raphson, when you choose the set S carefully, you construct a constant C such that it is a contraction mapping, and that's how you prove Newton-Raphson works. The details of constructing the set is tedious and would take us, I don't know, 40 minutes, so we're not going to do it. Okay, questions on these comments? Just trying to get the sequence ideas put in. We're going to add today a couple more notions to this, but if you use this as kind of your guideline to sequences, it'll be pretty good for your notes on the final exam. Yes, question?
Can C, actually, never mind. I was going to ask if C could be greater than 1.
No. In that case, the things could be expansive, yeah. So C has to be smaller than 1. So it's kind of like geometric, you get how you generate geometric series. Okay, so today we'll add a notion of a subsequence, which is just a special kind of subset of a sequence, and then we'll have the notion of a compact set, which is kind of cool. Okay, we left off on Thursday with the notion of a continuous function. So here we have a function that goes from one normed space to potentially another. It could be the reals, it could be some other infinite dimensional space, you know, it could be like differentiating polynomials to polynomials, who knows, okay? It's a function, and we can put a norm on this vector space and a norm on this vector space, and the norms can be different, especially if this is infinite dimensional and this is finite dimensional. They'd be different, okay? So in general, X and Y have different norms, and I just put 3 bars on Y. If you want to put a little subscript on the X norm and then 2 bars and a little Y subscript there, you know, all of that would make perfectly good notation as well. Then we say a function is continuous at a point. So we finally defined what a continuous function is after using them as examples all semester long. It's continuous at a point if you give me an approximation error, no matter how small it is, for every epsilon greater than 0, I can find a delta that is positive. As I change x0, delta could shrink. As I change epsilon, delta could shrink, but it's always positive. Such that if I take points that are within delta of my point x0, the value of my function is within epsilon of f at x0. Okay, so you tell me how close I want the function values to stay. I can always find a positive delta, so that if x's are within that, I don't exceed that error in the function values. Okay, so this is the norm in y, this is the norm in x. That's continuity. X within delta of x0 means x is in the ball of radius delta about x0, the open ball, because it's strictly less than. And this, you could say f of x is in the ball of radius epsilon of f of x0. It's sometimes a little bit dangerous to use this notation because here you forget what the norms are. Whereas here you see explicitly the norm. That's the only thing to be careful. And then it's not uncommon to see mixed. X in the ball implies this condition is true. They're all equivalent. They're all equivalent. You just need to keep in mind what is the norm being used to determine distance. That's all. Okay, and then a function is continuous on a subset, or that could be the entire vector space X. Okay, is continuous on S if it is continuous at x0 for every point in the set. So just definitions. And then what I asked you to do is to negate the definition of a function being continuous at a point. Does that work out? Nobody failed at doing that, right? If you didn't attempt it, you didn't fail at doing that. So I'm trying to be as inclusive as possible. Okay, so we kind of did it orally, and we'll write it. I've got it written down here, but let's do it again. So if we're going to be discontinuous at a point, that means there is some positive epsilon such that no matter how small delta is, I can always find an x that is that close to x0, and yet the function values are not within epsilon. There's a jump. Okay? I can always find an epsilon, there exists, such that no matter how small delta is, I can find an x in the ball such that f of x is outside of the ball, not in. Okay, so negate, it's there in the notes. Discontinuous, for every go to there exist, and there exists goes to for every. Okay, and so I can always find an x that is arbitrarily close to x0, and yet my function values, I should say greater than or equal to epsilon, when I negate strictly less than. Okay, so I failed, minus 10, okay, for Grizzle. And then here's the picture. This function fails to be continuous at x0 because I can find an epsilon. In this case, 1.0 works. Here's 1.5. Here's 2.5. That's still less than this, okay? Then, no matter how small delta is, as long as it's positive, I can get a little bit over here and I'll get function values that I can find x's within the ball such that the gap in the function values is at least epsilon. So that's discontinuous. Okay. We good with the concepts? Want to review anything on the concepts? We're going to keep building and building and building until we collapse at the end of the term from exhaustion. No? We're good. Okay. Wow. Now, here starts my beautiful handwriting from when I stand up. Okay? Theorem. And this is in homework number 10, problem 3. So let x and y be normed spaces. That f takes x to y be a function. Okay, so what we're going to do is write down two results that translate the definition of continuity and being discontinuous into properties of sequences. So the first result says A. If f is continuous at x0 and xn is a sequence such that xn converges to x0. Okay, so we take a function that's continuous and a sequence that converges to the point at which it is continuous. Then the sequence f of xn, which is a sequence in y, okay, converges to f of x0. Okay. So if you have a continuous function at a point, then it preserves convergence of a sequence to that point. So this is a sequence in x. F of xn is now a sequence in y. If f is continuous at x0, then yn converges to y0. Okay, you'll often see limit n goes to infinity, f of xn equals f of x0. Function is continuous at x0, you can take the limit inside the function, is kind of what that's saying, okay? So just kind of think about it that way, because x0 is limit n goes to infinity of xn. So if it's with continuity, the limit comes inside the function. B. If f is discontinuous, at x0, then there exists a sequence xn in x such that xn converges to x0, but f of xn does not converge to f of x0. Okay? So here's how this result is often stated. So I've broken it down into the two pieces. But this is how it's often stated. F is continuous at x0 if and only if every convergent sequence in X is mapped by F into a convergent sequence in Y. So xn goes to x has to apply f of xn goes to x0. So that's writing out in symbols the same thing here. So f maps convergent sequences into convergent sequences, and it should go to f of the limit point. Okay. Okay, so sequences characterize convergence. Excuse me, sequences characterize continuity. But bottom line, sequences characterize continuity at a point. Okay, so open sets, if and only if complement is closed. Closed sets, if and only if they contain their limit points. So that's sequences characterizing closed sets. And now sequences characterize continuity. So all those things are linked by sequences. One property, you link these two concepts of open sets, open sets and closed sets, and then continuity at a point. Let's just look quickly at the picture to see why the various parts of the theorem are true. So if our function is discontinuous at a point, how can we construct a convergent sequence in X such that when I apply F to it, it doesn't converge in Y? Well, start out with one point on this side. Take another point on this side, but get closer to x0. Get closer here, and jump back and forth. Then the y values are epsilon apart, okay? So they're not converging. They're just jumping back and forth. That's how you construct the sequence. If you take a point where the function is continuous, okay? If things are in here, they stay in here. So you just have to work through the definition of continuity. Continuity says there is no gap, there is no jump. So continuity says if I want to be within a approximation error here, I can put a ball here. And so I build my sequence that way. Okay? So just writing down the definitions, you can get it, but this is how you construct the sequence. I get closer and closer and closer and closer here, but these values are jumping back and forth, so can't converge. So if there's no gap, you can't build that sequence and every one of them converges. That's basically it, okay? So, cool. Are we good with this? Because we're about to dive off the deep end. Okay, we're going to do sequential compactness and extreme values of functions. Ooh. No, everybody, don't need to review? Okay, so let's do it. We're going to do subsequences then. Definition. Let xn be a sequence. Let 1 less than or equal to n1, strictly less than n2, strictly less than n3, strictly less ... be an infinite set of increasing integers. Xn sub I is a subsequence of Xn. Okay. Subsequence. Okay, so every one of the elements here is an element of Xn, but yet maybe I'm taking only the odd integers, x1, x3, x5. Or maybe only the integers, only the even ones, excuse me. Or maybe I'm going every fifth one. Or I don't have to have anything regular. I just need a strictly increasing set. So I'm just taking some of them, but No matter how far down I go, I always take another one. Then I take another one. So note, Ni is greater than or equal to I. Well, that's assuming Xn starts at 1, okay? So 1, what did I say? Yeah, N1. So if I take that to be 1, 2, 3, 4, 5, so otherwise I go 1, 3, and all of a sudden I get this is strictly bigger than I, okay? So it's just when you're making estimates and you know something about Xn and you have a subsequence, then if you've gone out a certain distance in the sequence Xn, and if you go to end of that number, you've gone that far out in the subsequence as well. Okay, so just tells you about that. So lemma. Suppose Xn converges to X0 and Xn sub I is a subsequence of Xn. All the points in the sequence Xn starts piling up around X0, and you take a subsequence. So its terms are marching farther and farther down, just like this one is. What does this subsequence have to converge to? The original limit, okay? If you just throw away every other term, it doesn't change the fact that I'm converging, okay? So if X1, X2, X3, X4, and then if I look at X1, X3, X5, X11, I don't know, it's X13, let's do all the primes, that still gives me a subsequence that converges to X0. Okay, so if you just write down the definition of convergence and use this property, you will be able to prove this. Okay, so just a good way to practice the definitions. Okay. Here's a handy inequality I'm going to want in a little while. For every x and y in x, the norm of x minus y is bigger than the absolute value of the norm of x minus the norm of y. So if the norm of x is 2 and the norm of y is 3, the norm of x minus y is at least 1. Okay. Let's just check really quickly why that's true, and then I'll use it in a little bit. You go, that's obvious, okay? So if I do the norm of x, that's the same thing as the norm of x minus y plus y. And that's less than, by the triangle inequality, norm of x minus y plus the norm of y. Okay? Everybody's good with that? That's just triangle inequality. So I'm going to take this, keep it, and this, take it to the other side. So I get norm of x minus y is bigger than or equal to absolute value of norm of x minus the norm of y. Okay? Bigger than or equal to. Now, the same argument gives if I had just written down the norm of y first, I'd have this. Norm of x minus y is bigger than or equal to. Okay, so there's nothing magic about putting x first. I put y here, and then I do minus x plus x. I still get norm of x minus y and have plus x here. And so I get this version of it, where I just swap x and y. And swapping x and y, there's a minus 1, but that doesn't change anything because I take it out and I get plus. I get absolute value of that, okay? But this is minus this. So I get that the norm of x minus y is bigger than the absolute value of norm of x minus norm of y. Bingo. Okay. Okay, so this will be really useful in a little while when we are making estimates and I'm trying to construct sequences that can't have any convergent subsequences. Okay, so if the norm of y is the norm of x plus 1, then the norm of x minus y is at least 1. Okay, so if I keep the norms and the terms growing, then the sequence can't converge because their distance between points can be bounded by how far apart the norms are. So it's a trick for building sequences where these can't get small because they're upper bounded by the difference in these norms of the terms in the sequence. So I just make the terms get bigger and bigger. There's no convergent subsequence. Okay. Cool. So I'm going to make a definition now. Let X be a normed space. Then a subset C contained in X is compact if every sequence in C has a convergent subsequence. With limit in C. Okay, so as far as being a magic tool, this is a little bit like completeness. Completeness said every Koshi sequence has a limit in the set. Okay, this is weaker because here we take any sequence. Well, it's weaker and stronger. We take any sequence. We can't assert that an arbitrary sequence has a limit, but we assert that we can construct a subsequence of it that does take a limit in C. That's what I said. We're taking a dive off the deep end. Okay? Every sequence in C has a convergent subsequence with limit in C. Okay, so remark, it's also called sequential compactness. We'll just call it compactness. So it's often called sequential compactness. Okay, so when we had the notion of completeness, it was super empowering to know that all finite dimensional norm spaces are automatically complete, so it's very easy to check. Any closed subset of a complete space is complete, so there's simple ways to check that property, okay? So, we have two results that we want. It can be done in any order. I was thinking of changing the order from what I did last year, but maybe I'll let you guys decide. So, one thing we can do is we can prove the following theorem. If a norm space is finite dimensional, then a set C is compact if and only if it is closed and bounded. So bounded, I can stick it inside a ball that's finite radius. Okay? So that means checking sequential compactness, as it's often called, is trivial in finite dimensional spaces. Sets closed and bounded, every subsequence has convergent. Every sequence has convergent subsequences with limits in the set. Okay? So that's one thing we need. The other result is even if X is infinite dimensional and you can establish this sequential compactness property, if I take a function from the set to the reals, it always has max and mins. Okay, so we can always do sups and infimums under any condition, but remember the existence of a max and existence of a min, that's something takes a lot of work to establish when we're doing the projection theorem. Does there exist something that achieves the infimum? That's the minimum. So this is another tool when you're doing optimization. If you're minimizing a continuous function over a compact set, there will exist at least one minimizing point for your optimization problem. Similarly, if you're trying to maximize the function, there will exist at least one point that achieves the supremum. Okay? Both proofs are fun. Which one do you want to do first? Or are you going to let me choose? Do you have a choice? Sabrina, which one? Surprise me? No, sir? No? Christine, you care? Joseph? Nobody cares? The closed and bounded implies compact. That's the way we did it last year too. But so that's what we'll do. Okay? I thought it'd be more fun to show that compactness is useful in terms of something concrete like an optimization problem, but it doesn't have to be. We can do the other one. Okay, so let's do compact if and only if closed and bounded when you're in a finite dimensional space. Okay, so bingo. Definition first, then. Subset S contained in X is bounded if there exists some R finite such that S is contained in the ball about the origin of radius R. Exercise. S is bounded if and only if I take the supremum of the norm of X over all X's in S, that is finite. It's exactly the same thing, okay? Okay, so there's some limit of how big the terms in S get in terms of, well, the norms of the elements of S get, okay? Now, okay, here's a fun exercise, and I really mean it. Fun exercise. S is unbounded if and only if there exists a sequence xk such that for every k bigger than or equal to 1, the terms of the sequence are in S. And the norm of xk plus 1 is bigger than or equal to the norm of xk plus 1. Okay, so that's our first step. Just talking about bounded sets before we get into the compactness part. Everybody see how this would go? To start out with any particular element, it has a norm. Elements in S have norm that's arbitrarily large, so there always exists a point in X whose norm is at least the norm of that element plus 1 added to it. Otherwise, all the elements in S have norm less than or equal to norm of x1 plus 1. And then just do it by induction, okay? So just a good practice with induction. Also, fun exercise. For every p bigger than 1, the norm of xn plus p minus xn then is bigger than or equal to p. This looks hard until you translate the n plus p over here bigger than or equal to the norm of xn plus p minus 1 plus 1, bigger than or equal ... norm of xn plus p, okay? So plus our handy inequality. And then conclusion, xn has no convergent subsequence. Okay, because with this sequence we've just built, you know, put some ni here, put some nj here, they're bigger than or equal to 1, every single one of them apart, okay? So sequences, all the terms are far apart, so any subsequence you have, they stay far apart. So, okay? So this is a way of just playing with the fact that if a set is unbounded, there always exists these nasty sequences that have no nice subsequences. Okay, I cannot construct a subsequence of this that's converging because all of the terms are bounded away one from another by at least 1. xni minus xnj, that norm is always bigger than or equal to 1 when ni and nj are different. No convergent subsequence. So play with that, with the handy inequality. Okay. Bolzano-Weierstrass Theorem. In a finite-dimensional normed space, let's write it like this. We haven't done this for at least a month. TFAE, okay? The following are equivalent. It's only 2 of them, but still. For a set C contained in X. A. C is closed and bounded B for every sequence xn in C just to emphasize the elements are in C, okay? There exists x0 in C and a subsequence xni of xn such that x in sub I converges to x0, I goes to infinity. Okay? So sequential compactness, or just compactness, in a finite dimensional space is equivalent to closed and bounded. Okay, a chance to write that down. Okay, we'll do A implies B first, and then we'll go the other way around. Okay, I wrote it, but I didn't say it, okay? A implies B. So, the image is so easily turned into a proof, you just have to get your notation right. But what I want to have ingrained in you is the idea, and it's all in a picture, okay? The picture has the entire idea. You just got to turn that picture into notation. So let me do the picture. Images. Today, bingo. Images, today. Beautiful, well placed, good enough, yep. Okay, so case one. Take our sequence. Suppose it only has a finite number of distinct elements. Okay. Case one. We have a sequence, and suppose it's built from only 4 vectors, and I'm just alternating between them in some way, okay? There's only 4. If you want it to be 404, I don't care, I just don't have that many fingers, okay? So, we have a sequence that has an infinite number of elements. There's only 4 distinct values. Theorem, at least one of them is repeated an infinite number of times. Correct? There's only a finite number of these, and a finite number of these, and a finite number of these, and a finite number of these. I don't have a sequence. So one of them is repeated an infinite number of times, okay? So, hence, at least one value is repeated an infinite number of times. Okay, so I gotta squeeze it in here a little bit, but say that is x5, okay? then there exists n1 less than n2 less than dot, 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 less than nk less than dot, dot. Such that xni equals x5, I equals 1, 2, dot, dot, dot. Okay, so one of the elements, I just said the fifth one just to be fun, is repeated an infinite number of times. So there's my convergence subsequence. It's a constant, okay? Anybody doubt that that one converges? No, okay? Hence, xni converges to x5 as I goes to infinity. Okay, case 2. Xn has an infinite number of distinct elements. Okay. Okay, so there's an infinite number of elements, and so I just kind of like, I map out these things. Now my set is bounded, so it has a lower bound and an upper bound. And it's finite dimensional. So take this to be one of the components of X. Or if you want to think about it in the plane, it has an upper bound and a lower bound. There's an infinite number of elements. So if I divide my set in two, theorem, at least one side still has an infinite number of elements. Everybody get that? It can't be that both sides only has a finite number of elements for the same reason that if I had 4 distinct values, one of them is repeated an infinite number of times. Okay? So I divide the set, and one side has at least one side. It could be both. If it's both, just choose one that has an infinite number. Don't do that. Go back down. Stay. Do this. Okay, so I choose this side arbitrarily. But the picture says this only has finite, but I don't care. So now I have another bounded set that's half as big as the previous one. Half as important. It has an infinite number of elements. Divide it in half again. Either the left side or the right side has to have an infinite number of elements. It could be both. Okay? Here it's showing maybe it's the right side. Okay? So I choose this half. And I just keep doing this. One of the sides is going to have an infinite number of elements. If it's both, just choose one. And the diameter of this set shrinks by 2 at each time. So, my set is closed, so if I get a sequence where all the points are piling up, I get a limit in the set. It's closed and bounded. I use the boundedness to divide it by half and have the diameter of the set have this geometric sequence. And so the boring notation is just to say, what notation do I need to have an index that says I chose the right side versus the left side when I divide the set in half? And if it's in 2 dimensions, do I take the upper quadrant, this quadrant, this quadrant, or this quadrant? One of them has an infinite number of elements. If it's 3 dimensions, it's one of the 8, okay? But it's finite, okay? And so I just choose one of those things that has an infinite number, and I cut the volume down by at least 2. Then I do it again, and 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 I can always go back now and choose elements of those boxes, and it's a Koshi sequence, and it converges, okay? That's the A implies B. Isn't that pretty? Want me to do it again? It was so beautiful. right? There's two cases. I only have a finite number of distinct elements, and so I build a constant sequence with one of the elements that's repeated an infinite number of times. That's trivial. It's a subsequence. The other case, it has an infinite, and the set is bounded, so I keep dividing it in two, and I just choose left half or right half of that, left half or right half of that, left half or right half of that. And so get a geometric sequence that's decreasing by powers of 2. I just keep track of those indexes. Then I go back and I know that I can choose elements from those sets because they have an infinite number of them. I just choose one, and then that sequence is going to converge because the geometric sequence 1 over 2 to the n converges in the reals. So that's A implies B. Closed and bounded implies sequentially compact, which we just call compact. You believe the proof? I mean, it's true. I'm not pulling a fast one over you. Now, why do you need finite dimensions to make this work? Is, think about this as being the argument on the x1 coordinate. Then I take those indexes, and so now the x1 coordinate is working out really well. Now I go to the x2 coordinate, et cetera. So if I only do that a finite number of times, everything is fine. But if I have to do it an infinite number of times, I could run out of elements, okay? So this is only for finite dimensions, and you can see how it would work in R2. One of the quadrants, say this one, then I divide that quadrant, then that one, I divide that quadrant, et cetera. So then it keeps shrinking. Okay. Cool. So A implies B. That's a picture. Now, B implies A. That's the hard part. So, we do not A implies not B. So this is good practice for us. What is not A and what is not B? Okay, so what's the theorem? A, C is closed and bounded. So not A is, C is either not closed or not bounded. It doesn't have to be both, okay? If you have an and you do the negative, you get the or. So, C is either not closed or not bounded. And not B, there exists xn with no convergent subsequence. Having a limit in C. Okay. Case 1. C is unbounded. Proof. your exercise, okay? So that's the exercise over here. C is not bounded. I can keep building elements in C whose norm strictly increases. That means as I go farther and farther down the sequence, they're getting larger and larger in norm with respect to this. And then with our handy inequality, the norm of xnp minus the norm of xn is greater than or equal to p. So no matter what subsequence I choose, it can never converge, okay? It can never even be Koshi, much less have a limit. Okay, so that's your exercise. Case 2, okay, so C is not closed. How do we produce a sequence that does not have a subsequence with a limit in C? How do I do it? In C, yeah. So C doesn't contain all of its limit points. So there's a limit point of C that's not in C. Okay? C is not closed. And C does not contain all of its limit points. So what does it mean that C does not contain all of its limit points? Is that there exist x0 in X and xn with xn's in C, and xn converges to x0. Okay, so I can construct a sequence that has elements in C but does not converge to something in C. Oh, I didn't say x0 is not in C, okay? That's what I really wanted to write. x0 is not in C. It's always in X, okay. So now what happens when I choose a subsequence of this? If a sequence converges, all of its subsequence converge to the same point. So every subsequence of this converges to something outside of there. So there's a sequence which does not have a subsequence converging to a point in C. So all subsequences xn sub I of xn, hey, you guys are getting the hang of this, satisfy xni converges to x0. Hence, we have built a sequence xn for which none of its subsequences have a limit in C. So we're done. Okay, so if a set is unbounded, we can build these sequences whose terms are all arbitrarily far apart, and hence there's no convergent subsequence. And if the set is not closed, we can construct a sequence always such that none of its subsequences have limits in the set. So either way, the set is not compact. Okay, so we've completed the proof that not B implies not A. I mean, excuse me, not A implies not B. So we've done A implies B, and not A implies not B. So we have if and only if A and B. They're equivalent, so it's super cool. So in a finite dimensional space, closed and bounded sets have the property that you take any sequence constructed from this set. There's always a limit point, a point in the set, and a subsequence of the xn's that is converging. So I can always construct from really bad algorithms convergent subsequences. Okay, so questions? Otherwise, we're going to stop here. And then on Thursday, we'll do the proof that if a function is continuous, the set has the compactness property. We don't care about the dimension. It's just that it's only in the finite dimensional case that we have this easy characterization of compactness. Just like it's only in the finite dimensional case that we have a really simple characterization of completeness, if and only if the set is closed, okay? So we have general conditions, and then we have specific cases that help a lot of engineering problems where we can check the conditions. That's the idea I'm trying to impart on you. Okay, so Thursday we'll do the fact that continuous functions on compact set have minima and maxima. They have always achieved their extreme values. That's it. Thank you.